Hello everyone, in this recording we'll discuss interactivity and dimensionality reduction. So dimensionality reduction gives you a kind of overview of a dataset. It shows you how samples are related and features are related at a very high level. So it's very natural if you have the overview to want to look for details. In this situation, interactivity can be helpful, right? The dimensionality reduction gives the overview. You can query for specific details based on some interactivity. So let's look at a simple example of this. Here are the same UMAP projections from the last lecture. I've just added a brush so that when I draw the brush, I both highlight the points and I populate this table below. Right, so now you can imagine if I want to look up any details about these samples, I can go refer to the table. Okay, and then it's just like any other kind of brushed scatter plot. As I go to different regions of the plot, I can look up details for the different parts that are highlighted by the brush. Okay, so this is this part of this diagram. This diagram is summarizing all the different ways that interactivity can be used in dimensionality reduction. It's in the reading for this week. What we just discussed is data manipulation, right? You can highlight, you can filter, you can annotate by interactively querying. You can also do feature manipulation. I'll give an example of that below. And you can even change the parameters of the algorithm. This is not so obvious an idea, right? But there's no reason that you have to fix your dimensionality reduction in advance. You could say, depending on the user's interest, you can adapt your reduction. So just to illustrate that last idea, here's a dimensionality reduction of the antibiotics dataset. So this is showing bacteria abundances over time for 3 different people. There's person D, E, and F. This is just the PCA, so you can see person F is kind of moving over time in this trajectory. And I've linked this dimensionality reduction with a plot of some of the species that are contributing. So here's just the top 10 species or top 5 species for each individual overall. What I can do, I can brush over samples, and then it's going to highlight the 5 most abundant species among the samples that I've brushed. And so here I brushed a lot of sample D or person D. So I'm seeing a lot of the bacteria for person D. Now, so far this is just like before, but what I haven't mentioned is that these aren't the original time series. And this projection wasn't done on the original data. This projection was done on a smoothed version of the time series. So you hope that the smoothing maybe denoises the original series. If I reduce the amount of smoothing, then I get a pretty different plot. Okay, so this is the original when I don't smooth. Right. And you can see a little bit noisier, but this is kind of the original data. Right. And if I smooth more, okay, now you see these kind of very smooth trajectories, and it makes sense that they're smooth trajectories. We've deliberately correlated everything by smoothing it out. Okay, some more variations. If you're ever having a kind of classification problem, right, you might imagine you get the dimensionality reduction just to see an overview, but really what you would like to have is some kind of automatically generated label for different groups of samples. You can try to do some sort of interactive labeling by first looking at the projection. This is much easier. It can be much easier to label this global overview rather than trying to look at each table. If you use a method that's able to adapt the reduction based on the new labels, that can make it a very efficient, it's kind of a virtuous cycle. The faster you can label things, the better your dimensionality reduction gets, and the faster you can label that. Another idea, you can try interacting with the features rather than the samples. So here's a figure, also a screenshot from the reading. This is the original PCA, and what it's showing here are all the columns of the original dataset that contribute to that PCA. So in reality, each principal component direction is a linear mixture of all these original underlying features. What these sliders are letting you do is it's letting you dim, is the term they use. It lets you kind of modulate the contribution coming from that feature for that overall principal component view. The idea is like MCG, if I reduce this all the way down to 0, then it's essentially showing you the principal component reduction or principal component analysis as if you didn't even have that feature. Right? So you can see how influential are the different features interactively just by toggling these sliders. Okay, some other idea, you can try choosing between different dimensionality reduction procedures, right? So there's no reason you need to settle on one algorithm in advance. You can try a few and I'll let users toggle between them. Here's a figure that summarizes all the different kinds of interactivity you might try to implement. So we've mainly focused on this selection operation, just like brushing. But we mentioned you can label things, you can move things around. This is very useful if you want to do some sort of robustness analysis. You might move the value in the original space and see how does the PCA change. You can do different kinds of drawing too. Right? Maybe you want to circle a group of points and then highlight that. Okay, one of the high-level points I want to emphasize. You will often hear people talk about different dimensionality reduction methods in some sort of machine learning or kind of methodological context without really talking about the visualization, and vice versa. When you hear about visualization conference or class, maybe not talk about the mechanics behind some of these reduction methods. But this is a very artificial distinction. The ultimate goal is to be able to learn something in a kind of more exploratory way. These algorithmic and interactive aspects are very dual to one another. Right? Any progress you can make in being able to manipulate the data can actually inform the algorithms, and vice versa. A better algorithm can actually make a better interactive interface for the user.